Time for another mini lecture to talk about common acid-base reactions. Some of these were described in class, but let's make sure they've been conveyed more carefully. The most common one that you would think about in terms of acid-base reactions are those things we describe as acid or exchange reactions, where you're swapping partners between cations and anions, yielding water and a salt. And the easiest ordinary reaction that has that pattern that you've probably encountered by now is where the hydroxide ion of some base is being neutralized by the acid. HCl with sodium hydroxide giving, oops, that's a typo, sodium chloride and water. Water and a salt becomes a very simple reaction process that we describe as neutralization. The complete ionic equation for this process, if you think about it, has aqueous hydrogen ions, aqueous chloride ions, aqueous sodium ions, aqueous hydroxide ions, and the result is aqueous sodium ions, again aqueous chloride ions, and water, which is a liquid as a product. If you recall how we handled net ionic equations once upon a time in a chapter long ago, we can come up with a net ionic equation by omitting those things which are spectator ions, and the spectators, I will note them with an asterisk, so the spectators that will be omitted are the ones that haven't changed from left to right, and if you're ahead of me and paying attention, you'll catch which ones they are. The chloride ion is 1 because it looks the same in the reactants and the products, both times aqueous, and the sodium ion is the other in this particular example, still aqueous from start to finish. The consequence is that the net ionic equation for this neutralization process combines a hydrogen ion with hydroxide to make water. Well, that sounds simple enough, but neutralization reactions with hydroxide will most often have some very similar or exactly that net ionic equation. Hydrogen with hydroxide ions combining to make water. So we can do this with other acids and come up with something else that's similar. What we'll do is we'll try one with nitric acid and potassium hydroxide. In this case, we're going to think in terms of swapping cations and anions, which is really quite straightforward and something you've done before, so don't lose track. And so the hydrogen ion is going to combine with hydroxide. Well, guess what? That's water. And the nitrate ion is going to combine with potassium, and that gives you potassium nitrate. If you recall anything about phases, hydrogen hydroxide, oh yes, water is a liquid, and potassium nitrate is going to have its solubility determined by the fact that potassium is always aqueous and so is nitrate. Simple enough. So that is an aqueous product. If you wanted to look for an ionic equation, or could think about this and recognize spectators without having to write them out, I'm thinking you might here. The spectators are those which begin and end in the same phase, and so HNO3 nitric acid is aqueous, and that means both of its ions are in aqueous phase to begin with. Potassium hydroxide has both of its ions in the aqueous phase to begin with, and so the spectators, I'm going to mark with asterisk again, are going to be those that stay in begin and end aqueous. Nitrate will be 1, and potassium hydroxide is aqueous to start to finish, so namely the potassium ion is the second spectator in this reaction. So again, the net ionic equation for this process with a different acid and a different hydroxide base, but still hydroxide base, is still hydrogen combining with hydroxide to make water. Not so bad. Okay. Another reaction of acids that interesting to note of acids and bases, it's a different type of neutralization, but it's with something that gives you more kinds of products. This is a swapping of cations and anions. Again, if you're looking at the reactants, it helps to see it in that respect. You have hydrogen chloride, or HCl, aqueous hydrochloric acid, 1 cation, 1 anion, combining with sodium hydrogen carbonate. And you can think of that as 2 cations if you wish, and a -2 carbonate, either way you want to do it. Or you can think of hydrogen carbonate as 1 ion, but it comes out the same. And this time when we swap the cations with the anions, you're going to get hydrogen carbonate combining with hydrogen ion or carbonate with two hydrogen ions to result in carbonic acid, which is aqueous. And sodium chloride is what you get if you combine the other pair of anion-cation when you swap them in this example. Well, that's sodium chloride. No problem. However, hydrogen carbonate is a very unique compound because of these things that we run into. This one is very much an unstable compound, and it will immediately turn into water and CO2. Water is, of course, a liquid, and CO2 is a gas. So that makes for a very unique feature in these reactions. Whenever you have a carbonate or a hydrogen carbonate, then you will find CO2 in the product, CO2 and water. The sodium chloride is still there as a product, but the net equation leaves out spectators as usual. And so the chloride is a spectator because it was aqueous from start to finish. And sodium was aqueous from start to finish, another spectator. And so the sodium chloride is ignored. And the consequence is the net equation is the combining of a hydrogen ion with hydrogen carbonate to make water and CO2. So this is a second type of acid-base reaction where you form a gas and a liquid, namely water. I didn't forget, they labeled that one right away. And it's one kind of reaction of acids that is used for testing with carbonates in rocks. Marble is a carbonate, calcium carbonate, and limestone contains calcium carbonate, so you can use these type of things to test for their being carbonates by sprinkling some acid on them, and you will get the bubbles of CO2. It's exactly the same thing you get when you put acid like vinegar with baking soda, makes lots of bubbles, or vinegar on an eggshell. Vinegar on an eggshell does exactly the same thing, making lots of bubbles, the carbon dioxide. The pictures shown here represent statues that have deteriorated as a result of acid rain. Acid rain reacts with these statues and dissolves away part of the rock or part of the sculpture, which is one of those unfortunate environmental hazards, environmental consequences. All right, so let's pick another one. Let's do another one here. Let's do hydrochloric acid this time with marble, calcium carbonate. And you would, yes, definitely get these kind of bubbles, but let's look at the reaction and balance it. So HCl is aqueous, can be very nicely aqueous. Otherwise, it's going to be a gas and you wouldn't want to deal with it. And then we're going to react it with calcium carbonate. We're going to write and balance this reaction and figure out what happens. Now, calcium carbonate is a solid. Oh, pay attention to this. This is a reaction where you're putting a liquid on a solid, this aqueous HCl, and then we're going to get some new products. So what will we get? Swap the cations and anions again. Calcium is group 2 element, +2 charge. The carbonate is -2, which it always was, and sometimes we forget. Hydrogen ion in HCl is a +1, chloride is a -1. So let's swap the cations and anions and make balanced formulas on the product side and then see where it takes us. So the hydrogen ion on the left, +1, with the carbonate on the right, it's going to take 2 of those to make that balance out. We'll make it to H2CO3, which is again that carbonic acid that you see at the top of this slide. Carbonic acid, which will be aqueous because this is an aqueous process. And notice that in order to have 2 in your H2CO3, that acid, there will have to have been 2 HCl to begin with. Notice this is the same one shown a little bit ago, the carbonic acid. The second product then is what you get when the chloride combines with the calcium. Well, think about that. Calcium +2 ion, chloride -1 ion. In order for the formula to come out correct and electrically neutral, the charge of one becomes a subscript on the other. So the charge of +2 on calcium becomes a subscript on chloride, and that is a compound that is soluble. Chlorides normally are, unless you put them with funny things like silver, mercury, or lead. All right, now, we're not done yet because we have to make sure this was balanced. The 2 on HCl accounts for 2 on the calcium chloride, so that's good. But it's not complete until we show the final state for the carbonic acid. I should write its name up here for you. I don't expect you to know carbonic acid necessarily, but I refer to it enough that I thought it would be useful to write down its name for you. Okay, it does not stay intact as H2CO3. It immediately dissociates in water, which is where you will only find this occurring, the only discussions we'll have, to make water. And what remains after you take that out, water plus carbon dioxide. So carbon dioxide is a gas, always, unless you get it really cold or under high pressure. But you've seen carbon dioxide as a solid. Its normal status in most operating conditions would be a gas. And then this other product is still the calcium chloride, as shown in our first pass of what this equation includes for products. Now, verify that all of this makes sense. Are there any spectators in this process? Well, think about that. Now, it's balanced. We checked that out. We had 2 hydrogens on the left, 2 chlorides on the right, 1 carbonate, and 1 calcium. So everything is okay in that respect. But is there anything else that becomes a spectator? Well, you could come up with another spectator, and the only thing there would be in this case is the chloride ion. But it doesn't seem very important to leave that out because it is the only spectator in this case, because chloride ion has to be present in order for calcium chloride to have charge the way it, or to be equally balanced formula. But just to write it out so you can see what you might get for a net reaction, it's not a lot improved, but the net reaction becomes what? Well, you should have the hydrogen ion, but there's going to be 2 in this case. 2 hydrogen ions reacting with the calcium carbonate, and that's a solid, so both of those things are going to change as a course of this reaction. Over the course of this reaction, they are no longer solids, but then they turn into something new. And so we list the status, the phase, of the calcium carbonate. And on the product side, we now have the things that are shown just above there, namely water, and which is a liquid, and carbon dioxide. As noted, the carbon dioxide is a gas. And the other product, if you could leave out a spectator, all that remains now is a calcium ion. So the calcium solid with the carbonate becomes a carbon dioxide, water, and calcium ions that are aqueous. Kind of funny to go from calcium solid to calcium aqueous, but this equation does still fit if you realize that there's a charge of 2 on the left side with the 2 hydrogen ions, and on the right side there's a charge of 2 on the calcium ions. So that still is reasonably consistent. All right, let's try another example. The third, another application, Another application of acids reacting with carbonates or metal carbonates is stomach medications. Oftentimes this is a separate type of neutralization reaction. These pictures are positively ugly in case you were wondering. When you have antacids involved in neutralizing excess HCl that the stomach secretes, that's exactly what is happening. You're using carbonates or metal carbonates, but sometimes also hydroxides, to neutralize the excess acid. So you can have things like magnesium or aluminum hydroxide, otherwise carbonates, either hydrogen carbonate or ordinary carbonate, and you'll get CO2 as a product if you use the carbonates to neutralize those things. If it's not sufficiently neutralized, you might have something ugly like a peptic ulcer, which can be very uncomfortable. Don't ask for one. Okay, third type of reactions of acids. And this is, again, proton donors and proton acceptors. Really, all of these are. And this has already been alluded to if you notice the other types of base and acid reactions that were described earlier, in describing earlier bases. So ammonia is the new base that in question here. And ammonia is a base because with 3 bonds on nitrogen, its octet includes a lone pair. And that lone pair is able to pick up another hydrogen ion. And so in this example with an acid like nitric acid, the hydrogen ion is picked up by the ammonia and turned into the ammonium ion. And so ammonia is a base, and it turns into its conjugate acid, ammonium. And the nitric acid is certainly an acid, but it turns into its conjugate base, the nitrate ion. In this case, the two combine to make an ionic compound as a product. This is described as an ammonium salt because ammonium is in fact the name of NH4+. So it's any old ionic compound that you end up with that's formed by the reaction of ammonia or its cousins that have some other thing like carbon on nitrogen, which will be discussed if you go on to Chem 116. And these ionic compounds with ammonium ion are very soluble in water, and it's very advantageous in many cases when you have an ammonium compound. So this compound on the left that's blue is, like we have seen in another example somewhere, it's a base that can pick up the proton from HCl. It turns into its corresponding ammonium ion, its conjugate acid, by picking up the proton from HCl. And HCl, therefore, is converted to its conjugate base, the chloride ion. All right. So, it's an ionic compound. A cation and anion becomes an ionic compound. Let's pick one more example to try with ammonia, and pick any old acid. Let's try not to get tricky. So let's pick something not very hard. Let's pick hydrogen bromide. All right, so if we do this, what will the products be? Again, ammonia is the base. The base will pick up a proton, and the result is you have an ammonium ion, which is always soluble, but it's also combining with what remained of the HBr, namely the hydrogen bromide or hydrobromic acid, becomes a bromide ion. And so giving away a proton leaves it as a negative charge ion. Oops, I didn't really put that in there. It has a negative charge that goes one each with the ammonium ion, and it's a very soluble product. Ammonium bromide is a very aqueous compound, very soluble. All right, looks funny because there aren't two products, but in effect there are, but they just combine in these descriptions to look like one product. All right, there's three types of acid-base reactions. One was neutralization with hydroxides, one was neutralization with carbonates, and the third type is ammonia as a base. I hope you find that helpful as you are working through some other questions. Good luck.